Welcome everybody. Yes, we are going to record you. So welcome everybody for this second session of the probability seminar this semester. So this is a double session, so it will be session 2 and 3 of 2.A and 2.B. So we have Joaquin called this the Revenant seminar. So we have two of our ex-students speaking here. So the first one is Felipe Espinosa. We'll be talking, who's now in the University of Münster with Chiranjeev doing his PhD, finishing the first year. And he will discuss about these dynamics of the thick points of the Gaussian free field.
Avelio, as the title says, we will talk about dynamics on something related to something. I assume, I don't know if anybody, all of you knows what is a thick point and what is a Gaussian free field, so we'll do like really quick review about this. But before that, I would like to say why we did this. And this started with like a really naive question, like a year ago. It was, we understand planar Gaussian free field and a bit of it. We understand some of its geometric properties, as some people know here. We wanted to know what happened if we put an evolution on these type of things. Like we understand the static situation, what happens when it moves. That's the whole thing. That's the whole reason why we are doing this. Nothing more prior. To start to like expand this, why this question means, let's start with what is a Gaussian free field, right? So there is like a really direct, naive way to define that is take a planar domain bounded with a, let's say, nice boundary, C1 boundary, and yeah, a nice good one, like from the PD people like to take, for example. And we take the C infinity functions on it, a compact subarc. And we say, okay, the Gaussian free field is like the linear operation that is a Gaussian process indexed by this big family and has a covariance given by the Green functions of the Dirichlet Laplace operator. This means that in the boundary, this is like the inverse of the Laplace operation when you consider the boundary equals 0. And obviously, if you try to think that this is the correlation between 2 points of a Gaussian free field, this usually diverges, and you can expect that the GFF itself is not like pointwise defined, but rather like a sparse distribution. So anyways, we can still kind of look at these type of things. Here is a simulation done by another old student from here, that's Thomas Langley. As you can see, this is not like a really nice picture. It's not like what you would expect to see when you want to think of a surface. It's like too spiky maybe. And one of the first things you can see is that there is like really high points, right? There are maybe things here that you cannot actually see because the things that captures your attention are these points, the highest ones. And this is actually what we want to study. These are the thick points, formally speaking. So in order to introduce these like things that when you want to define them, you need to do a small detour and try to define it point-wise. The above is an approximation. We want to maybe do another one. And here we will consider the standard one, which is take the harmonic measure of a set, and for a Brownian motion started at the center of a ball, let's say, and you intersect it with the domain you consider from the beginning. And you consider the measure related to the Brownian motion exiting this set, right? We will define this approximation with this index epsilon and x as the evaluation of gamma with this measure. At prior, I know this is not well defined, but at least for now, believe me, this is true. We can discuss afterwards why it's true. And with this in mind, we now have a function in let's say two parameters, this epsilon one and also the geometric or the space one. With this, we define the thick points. And we will say a point in the space is thick or a gamma thick if, if when you turn your modification parameter going to 0, it grows up as the logarithmic of 1 over this small parameter. So this, if you think about it, we're going to expect that this is somehow related to the variance of this process. So these are not typical points. These are weird points. and somehow really important for the GFF that we want to talk about it. Just keep that in mind. These are somehow the spikes we were seeing before. And small detail, we have defined a set, but there is nothing telling you at prior that this is well defined or it's empty or not. So in order to see that at least this is reasonable and not something pathological, we will need the following, which is also important to study the geometry of this set, which is first result from Humilier and Perez from 2010, studying the thick points. And it says how continuous is this approximated process. And it's actually like a Brownian motion of continuous, but you have to consider this like logarithmic blowout, but up to like a small scale. So with this in mind, with the things that we just saw, you can actually prove that this set is well defined because it's coming from like a continuous function and it cannot be that big. It has like a Hausdorff dimension bounded by something. It cannot be like the whole plane. It's not full dimension 2 if it's a positive number. And also, this is not empty up to 2. If you go after 2, there is nothing there. You won't see something in the space. And let's forget for a minute what happens exactly at 2. Let's just keep in this open interval. And okay, this comes from this continuity. And the natural question is, okay, this is the exact value of the Hausdorff dimension. So let's say we can conclude that it's never empty. The answer is, okay, we can actually prove this, but we need something more. We need a special thing, an important, let's say, machinery, which is called the GMC theory, which comes from like the 80s. Let me just present it. The Gaussian, if I say Gaussian multiplicative chaos, you think of the exponential of the field. And this exponential is defined with a certain rescaling, and it converges as a measure. It's not a function, it's not a metric, it's a measure. And you know it's unique. This was done by Berestik. This at least is done by Berestik in 2017. You can see later, or at least you can see more formally in another paper from Yuanaru in 2020 that this measure is actually really important for the things we want to look, because if you take the GFF, the Gaussian free field, and sample a problem from the bulk measure, this would be most likely a peak point. So we also know it cannot be empty, the set. We can actually find those points at least. And even more, it won't be a limit, so it will be the limit. And that's let's say a fun fact. With this in mind, we can use these classical potential theoretic arguments, and in Aru as well is at least you can find it formally. You can prove the Hausdorff dimension is what we want. We can obtain the lower bound. And you can see it's a fractal which is interesting at all. But what I want to like keep in mind for what we just saw is the following. If you give me a Gaussian field, something weird, we can do the following to understand these spikes, which is first find the regularity, do something like using the things from before to find an upper bound of the Hausdorff dimension, and then try to do the same as Berestik did and as well, and find this weird measure. With this in mind, I want to present you the first dynamic, which what we call it the Austen-Uhlenbeck Gaussian free field. This is because it somehow resembles a finite dimensional Austen-Uhlenbeck equation. Here we took some already like dynamic Gaussian free field in a way. We are like adding over the Gaussian free field, and we start with something independent of it, which is also a GFF, since we want to see dynamic behavior. And this is the important part of this. This is how it looks. I would like to keep a minute here because, as you can see, this is, I like to think of the sea. It's not oscillating a lot. It's moving quite nice. Okay, it looks nice. Let's see how nice it is. To do this, since we see this movement, we decide to define, like take a point and see how it oscillates. This is the thickness function. Instead of a thick point, it's a thick function. And here I have to do a small observation. This evaluation is only in space. You are not convoluting in space and time. So only considering this because recall we want the dynamic behavior. And we have this first strong result that what we saw is actually like that. this function is always continuous. So whatever thickness function you take, you know it will like at least won't do weird jumps. And this also gives you like a trigger corollary. Say at the beginning, these points are weird. So if I take something that doesn't have in consideration the GFF from the beginning or at any point, this will always see 0. So let's say like a point that started from 0 will never like go up magically.
And then like the idea is that the invariant measure of this process is the GFF?
Yes, it is the GFF every time.
Okay.
Sorry, I forgot to mention that. The invariant measure of this dynamic is a GFF.
Okay.
And yeah, this is always like continuously moving. So for example, you know that whatever you take as a big function is also like bounded. It's never like more than 2. I didn't put it, but we also know that these functions are like 1/2 Holder, all of them at the same time, with a maximus Holder constant equal like 2. With this in mind, we do, let's say, a small mental exercise. I already told you that with this measure, you can find thick points. So we will say, okay, what are the dynamics of these first conditions? And you can actually prove that it is given by this like nice exponential. You can index it the whole time because of this. The often dynamic is reversible in time, and so is this. So if you can do one way, you can do both. And this is actually really easy to prove because you can do the following. So I have my equation. Let's say phi is equal minus 1/2 phi plus my noise w, and I have my initial condition. Phi at 0 is gamma. And no, wait, sorry. This is not the way to prove it. I confused it with the next equation. But in this case, you can take the point. Let's say you sample the point from your measure, and you can check for the correlation between this and let's say the next point, which is you take it, so epsilon xt. Under this new measure, you can actually prove this is the same law. Let me put like calligraphic X to understand. That is equal, yes, equal in law this as an independent, the initial condition, epsilon at the same point, plus some with an exponential with exponential decayment, let's say t, plus something which is scaling like this, which is like this. Let me put a hat here, with another field which is independent of this one. So you can do this decomposition. Since this is independent, when you divide it by the logarithmic of 1 over epsilon, 1 over epsilon, and 1 over epsilon, epsilon is which direction? I think this has to go to 0 because this is independent of this Gaussian free field, and you already know that this will converge to gamma, and you have already the decayment of t, and this will converge as epsilon goes to 0 to my desired function. So with this naive argument, we can see only due to like a Artin-Uhlenbeck decomposition, you can see these type of things. You can do it for rational times, but you already know this is continuous, so we are done. Simple proof, elegant and nice.
So just to so here this equality is equal for fixed t.
For fixed t.
So it's not equal in law as a process.
Exactly.
It's equal in law because it's not realized.
It's equal. It's the same. Even let's say a positive time. If it's negative, we have to add an absolute value. But you can see that this is quite obvious. So there is like an answer, you can see it, obviously. You can see this like exponential decay as you will expect. Okay, now we can ask ourselves, we can find the exponential, right? What else can we find? Can we find, let's say, well, we know whatever we look at has the supremo, has to be 2, right? Because it's continuous and then every time cannot be bigger than 2 because it's like a Gaussian free field. So we have this, let's say, obvious observation, but maybe it's not the only thing we need. So there are like other examples. Can we find things with different spikes, like summing things like this. We can maybe find one or two, but how many can we? For example, and can we find weird things like a Brownian bridge condition to be inside these -2 + 2, let's say, conditions? Or can we find a constant function, something that is always at a given height? So this is our question of motivation, and to answer it, we need to add something extra. This b at most 2 is not sufficient enough. We need to add some energy constraint. As at the beginning, there was this energy constraint that you cannot be higher than 2. We need to introduce this energy. And the first thing you can prove, but it's not quite trivial, is that for every function that has decay at 0 at infinity and is not much energetic, like the energy that I just defined is less than 4, then you can find a point whose thickness function is given by this. So somehow this is all h of 1 of r. You can
you come back to the energy? Just to
yes.
Can you
Yeah.
explain why this energy appears?
Yes, sorry. It's fun enough. Look at this energy, think of an ODE. It's exactly the ODE of interest without the noise. So also a bit natural that appears. With this in mind, which is like somehow the energy of the equation itself we are studying, it appears that it also constrains you how is your thickness functions. And since you need a notion of derivative, you can also prove that this is equivalent to the h of 1 norm of the whole space. So yeah, you can be at least in some form of ball in this space. And even more, there is a corollary of this result that it tells you how many of these points are in the space, which are a lot, as you can see. But obviously there is the next question. This is everything I need. At this point, I don't know how to find a Brownian bridge yet. Maybe I can find constant functions if I control well the energy and I ask for the certain decay afterwards. And we have proven that it's not sufficient, it's also necessary. So for example, the constant functions, you can find it, but you have a constraint on how long is a constant function. So let's say if you want something constant between 0 and t, it cannot be really high if you want it for a long time. And even more, since it's a sufficient and necessary condition, you need to be in this regularity space given by Hölder space, by the Sobolev space. So the Brownian bridge cannot be there because it's not H1. So this is where here ends this dynamic. We kind of be happy, we understand how this fluctuates, and we saw it's really nice. It's not like continuous, it's also like kind of smooth, right? Because it's H of 1. And the next, so I would like to present quickly the next equation, which is like a classical like toy example of an SPD, which is the additive stochastic heat equation with a white noise and again something a Gaussian free field independent of the noise. This is how it looks. And you can see this is not as nice as the first one. This is quite radical, right? It's not smooth, it's not like they're appearing and disappearing. So let's keep what we saw first, which are the initial conditions. In this context, we see something completely different. If you give me a time, no matter how small it is, and I try to do like a thickness function in this context, the thing that was with a given height, the ones that I can find are going quickly to 0. And this is actually very easy to prove because it's, let's say, a property of the equation. You know that the stochastic heat equation has strong solutions. So, well, this is not this one. What is the other one? What is it?
Your friend?
Oh, yeah. It happens a lot. So notice this really trivial observation from like an ODE curve maybe. If you have this equation, this is obvious. You can obviously split this. Let's say you can split as the sum of the following two equations. You first consider the heat one with the noise, but no initial condition. Let's say 0 initial condition.
So you mentioned the Felipe. So this one also has the Gaussian free field?
Yes. they both have the Gaussian prefill as invariant law. Sorry for that. The thing I want to say now is, okay, with that in mind, we can continue with this part. We can split, obviously, as like the homogeneous part and the one with the kernel. And since this and this are independent, you can argue as before and split the solution in these two parts, and you use the regularization property of the heat equation to conclude that it has to be zero, because independence plus something that is already a function, so this part will go to zero. It's not blowing up.
Yes.
So-
Weird one in your argument, because somehow you have to say that for the first one, you don't have a tick point at a given point x.
No, but and the next one is not anymore. When you will have a function in the second one due to the
Yeah, the
regularization
second one you have a
property.
function, but in the first one, why is x not a tick point?
Because it will be independent of the initial condition. Because it will be a linear functional of the y
So you
naught.
have to prove that if you take a point independent, then it will not be a tick point for the first.
Yes, but we already proved that we say something independent of the Gaussian free field, and it's almost with high probability.
But the first one is not a Gaussian free.
Yeah, it's true. But it's also independent of the initial conditions. So it should be at least independent. That's how it is, how we remember to prove it. It's kind of a Gaussian free field, though, missing the up to a correction, let's say. And here it's a bit more careful with, if you try to do like an Austin-Uhlenbeck decomposition as before, you won't be able to do it without considerations of the only like time correlation. It's a bit more delicate due to the Laplacian. That's a comment. But this is in the spirit the way of proving this going to zero highly, because the tick points at the beginning are not, let's say, the noise is hardly hitting in a special way these special points. So with this in mind, you see, asking the same question like continuity, for example, or thickness function kind of lose sense. So we realized maybe we change perspective and okay, this is how it looks. At the beginning, this is somehow like, you can see that points that are high currently are not high anymore. So even in a simulation, you can see that you might expect not like continuity, for example.
I know I did the simulation, but maybe you can explain what the simulation is.
I know this simulation is at the you cannot see it, right? Sorry, here is a point at high 1.5, let's say, and you can see that there is no like a decay. Here is that it is gradually going to zero.
And what is the line at 0.5?
0.5 is something below that line is like being zero height, zero thickness function. Somehow this is due to the approximation, if I'm not wrong. Somehow this is like the order. So if you are inside this, you are not like visible anymore. And here, okay, you cannot see it because it's really going to zero real fast. So now we take the whole space and time domain. And again, we are not taking the convolution in time, only in space. It's not space-time, only space, because somehow we expect this way prevail the dynamic behavior. And just recall the beginning, we were following like a recipe. We need the first thing we need to understand is how this part of the field behaves in terms of continuity. And in this context, I would like to put it because we usually want to see like a norm, but here we need to add this like parabolic norm because of this like parabolic rescaling. How much do you form in time is not the same as in space, not the same order, let's say. So the continuity is given now by this, and this will give us really weird things, because if we do the recipe and we do the chaos and the chaos BMC measure and the box content argument type of stuff, we can again find the measure. I will explain a bit later the measure, because you can do it in a marginal way in this part. And we see that the Hausdorff measure here has something weird happening between 2 and at 2. So this motivates the following. Here we will talk about a regime, like a thick regime, because it's the usual one from the Gaussian free field. And in the next one, we will call it the super thick regime, because it's high, anomaly high. Because remember that in theory, this is always a Gaussian free field, but in between something weird happening. And you can actually see it here. You have the line, which is the maximum, like the how high can you allow to be, and near the end you will see things that are going beyond this line. These are like the super thick points, the thick regime, and it's appearing in some weird points. So the first thing Avelio proposed to study was, okay, what can we say about these times? Okay, we define this set of exceptional times, like there is something with super thickness height as this, as st, exceptional times. And we can see when you see it from the super thick regime that the Hausdorff dimension is like half of it, part of the. In a naive way, you can see it's part of the scaling that we saw in times, like 1 to 2.
So just the S is a projection. So what is the, because T gamma was the
this is this is like the formal way to say we took the original thick points and we're taking the projection in time. But this is
a subset of the real line.
Of the real line, exactly. So yeah, this is a subset of 0 and T, and yeah, this is like
if I take a T there.
If a T is there at that time, you can see in the stochastic heat equation a super thick point. You don't know where, but you know there is somewhere. You know there is somewhere. So this is like mathematically written, but it's the time where you can see something high. Like it will be something like 8 here. I won't. Okay, I already waited. So in that set, you will see this.
So what is being in the graph? So what is in the graph?
In the graph, you are seeing the maximum of the height. No, this is following a point that at some point is the highest. At the end, you can see it's the highest somehow.
I mean, if we were following a point, it would become to 0 now.
Yes.
So this is what you told us.
No, this is the one which goes higher because this is line 2.
Yes, so it's the maximum at every time. At
exactly.
every time it's graphing like it.
It's not the one at some point and then it's following it?
No, because not that one you presented before that goes to 0 now.
No, because in the one I presented at the beginning, the line was in 0, between 0.5 and minus 0.5.
Yeah, but started with the maximum.
Started with the maximum at the beginning. Here is the maximum, right? But it's following through time. Like it's maximum here, but it was not the maximum all the time. It was like below that at the beginning actually. But yeah, this is how it behaves, and this is the time we're considering. We can understand it, so we can, for example, see it's totally disconnected and stuff like that.
So there is something weird. You have a 2 minus gamma squared. Like
yeah.
When you put gamma equal to 0, that gives you 2.
No, but this is gamma between 2 and square root of 2 square root of 2. It's not for every gamma. This is for the super thick regime. If you want to see the whole from 0 to 2 square root of 2, you have to put minimum 1. Because you have to, this cannot be greater than 1, I think. So, since we saw this strange behavior, we decided maybe we have to look somewhere else, like what is happening there. So we now take the other way around. You give me a time in this weird set, and we see how it's the fever, the I don't know how to the set of points in space. Let's say the thickness here. So here is a mistake. No, yeah, it's well. You are seeing that for each time here are the thick points that were gamma thick at time tau. So in particular, expect these are like the points in space which are in the super thick regime, and we want to understand this set. The first thing you can say is like, okay, many points are there, and Avelio had the claim that it was finite, and it was hard for me to believe it, but you can see something like this. Like if you take a point in this set, the set is finite. And even more, if you take an n not big enough, let's say not bigger than this quantity, then almost surely you can find an exceptional time with that amount of points. So you can only like find, if you have a weird time, exceptional time, the amount of points that are really, really, really high is not many of them. So in the Hausdorff dimension, what we are seeing actually is like the times that are weird, those somehow.
So just understand. So the Hausdorff dimension of, if I fix a tau, a tau in a special time, then and in an exceptional time, then the Hausdorff dimension of the points that are gamma thick is 0.
Exactly.
Because they are finite dimension.
Exactly. There are none of them actually. There are not many of them. And we actually can see like the other way around. So if we start to see this, like you take the super tick regime, you take an n that fulfills this inequality, you can see that if you try to find like many of these points, let's say, can I find more than the quantity below? You will try to find them going to the GMC. So obviously, if you fix n equals 1, let's say, like try to find only 1 and avoid this condition, which will make sense, you will recover the GMC measure, right, for the stochastic heat equation. But now we want to find endpoints. We want to find as much as we can. So we have to construct this Liouville measure. So for each fixed delta at least, and we can prove that this exists, and it also gives you n tick points, but only if you have a maximum amount of number. So there is most likely the expectation that after that it's not true, and this is what we can see actually in the following proposition. So in the super tick regime, for each this set of weird times, the sets you can define. Okay, this is poorly written. I have to apologize. This should be the set. Oh yeah, sorry. I got mental disorder. If you take the points which are different and endpoints which are different, let's say D and T, you can see that if you don't take like many copies of T, you can find like points which are like distance of each other. But if you go beyond this inequality, let's say it's bigger than the other way around, then this set is empty. So there is in the fibers, the amount is finite is actually bounded, cannot be infinite in any exceptional sign.
So what is the delta here?
Delta is telling you how far away they are. So you say, okay, let's take the things which are at arbitrary distance. None of them will and rational. This will be not empty, but the same when you do the same thing here for some delta on actually will fail for every delta here. In particular, you can actually find how many has exactly a number of times, and we have the natural questions: how many things is this condition necessary? But we saw it's true. But nonetheless, we can find the last part of this geometry of these strange points when you want a number of big points, which is somehow the one as before, but you have to add this, let's say, punishment on when you want many of them, and obviously you are restricted to the thickness you want. So you can see again there is no times where you have n thick points. That's the last part. And obviously we like some questions we have because we have a lot of strict inequalities. So for the Euler-Uhlenbeck, we want to know what happens at energy 4. Maybe true, maybe not. Most likely yes, but it's not proven.
Maybe true what?
That at 4 there are thickness functions with energy equals 4. At least maybe we can even find them, but we don't know. And obviously,
we have one that has energy 4.
Not.
If you take the critical measure at the starting point,
yeah,
a point pick with that one,
it will be 4.
So we
no,
know
that's energy 0.
4. If you start at height 2.
I know, but it's energy equal 4. And
yeah, if you start at height 2, you have energy.
No, but the energy will be 0. The energy of the exponential decay is 0.
No, because you are doing this.
All right, yeah.
4.
Okay, then the question will be how many of these are. I apologize. And the other critical values are obviously the square root of 8, and this weird sequence of having endpoints with a given thickness, which funny enough converge to the original critical value. And obviously we will see maybe other things like the first factor set, the two-value set, or the level or flow lines. These are things I haven't think about, to be fair, just therefore if somebody gets excited about it. That's all. Thank you for your time.
Felipe, so are there any questions here on the chat?
No, una close.
Una close.
Is there any way to that? I'm wondering about this fact that there's only finitely many. No, okay, finitely many, that's okay, I guess. Maybe. But why this sort of sharp bound? There cannot be any more than.
Ooh.
It's
Yeah, it's weird. I'm trying to recall the good explanation why we have like a sharp bound on the number of it. It's not clear. I think it's related to at a naive level. I always say, but I don't know if Avelio agrees. Is you still have like a finite amount of energy in space when you're perturbing things, and points in the superterritorial regime are really, really, really energetic. You don't have that amount available somehow. So it's natural that if you have finite of them, as higher you go, it's harder to get even one. But as you can even see, at some point, there is only one really, really, really thick point near the square root of 2, 2 times square root of 2. And this is like the naive explanation of this. Funny enough, this constants is also appears somewhere else in related to certain phase transitions on the Ising model and the Potts model, or if I'm not wrong. This number has a name. They call Baraja constants, and we don't know why they appear to be there.
Cosinus of that.
Huh? The
It's a little
signs?
bit more subtle, but
Yeah,
so it's the cosinus of that.
It's like-
So I will maybe make a comment on that.
yeah.
So
Thank you.
just for this gamma n, so there is a relationship in statistical physics between Potts models or FK models and this gamma level for the Gaussian prefield. So it has to do with a certain cosinus. So this one only works for gamma when gamma is between 0 and 2. So it should not work in this regime, but one knows that gamma plays a role with kappa, and 16 over kappa, they are related by duality in SLE. So in this world, we just apply that formula. We try to relate them, kappa with 16 over kappa, and we see that these exact numbers corresponds to what is called Baraja numbers. So Baraja numbers are possible zeros of
Polynomial related to graphs.
so it's called color polynomials, or like polynomials
Colored
Ka-
polynomial.
that count the amount of colors that a graph can have, the amount of possible colorings a graph can have. So this relates essentially this relation with Potts model, but antiferromagnetic. So essentially, if you want to count how many colorings you have, you can put antiferromagnetic Potts model at really low temperature, and then you will get a coloring. You extend this to the real number, and you see that there is a phase transition on that. And this phase transition corresponds exactly to this gamma. And we have been trying to understand if there is a relation or it's just random, that everything somehow coincides. And it's not completely obvious because Potts model with a non-integer amount of colors is a weird thing, especially when it's antiferromagnetic, because in ferromagnetic you can work with FK calculation, but in antiferromagnetic there is not anti-FK, so it looks like it's really with the 6 vertex, but
Yes. So yeah, that's related to this exactly amount of thing. Yes. I don't know if there any other question.
so maybe what are the first passage sets and the two-value sets and all these things?
As I remember, the first passage set is the Gaussian free field being below, not above minus A, and the two-value set is the Gaussian free field being between B and A, minus A. But that's like a really naive explanation. We will need to talk about exit sets. And
Felipe, what other dynamics would be of interest in the GFF?
like for a real, like for
geometric properties, like the work that you did,
But-
and a set of tools that you tried with the.
no, but for example, you could try to do this same thing, but for the whole fractional setting here with the fractional corresponding noise. Will be like the first naive approach. You would ask for self what's going on with these same type of things between the zero fractional Laplace operator, which is the identity, and the 2 or 1, depending on how do you want to index, like alpha or alpha over 2. So you could like, for example, the thick points moving discontinuously in the whole positive fractional Laplace or in the middle. I believe it is for everything positive, because somehow as long as you have strictly positive, you will see different, like, let's say, if you try to expand it as a sum, you will expect seeing different velocities of mixing in the Fourier series for the coefficients related to it, in time at least. So that would be maybe another thing of interest, which is the in-between regime, and people care about that in general for physics reasons as well.
So maybe this is a stupid question, but in the last question you put in your future work, in a way you're saying that every time you have a domain Markov property, right? So, but do you have like a
which
Markov
one?
property in time of this type of?
In time, I think you will, at least like as a process, let's say in the space, I think you could say there is like Markov property in both linear equations, but like saying, yeah, I can take my equation and try to restart it and run the process from there and split the noise into independent ones due to the independence of the noise. But in a space is already not trivial made for each time, if I can explicit. And in the space-time domain, not true. Okay.
Yeah, regarding the measures, you have a measure for each time instant you can compute find this measure. Do you have some idea of the law of the process of measures? Can you say something about?
No, I wouldn't able to say anything. I believe we try to understand a bit of it, like even like basic properties as continuity, for example, and I wasn't able to prove, for example, the continuity in the classical regime. We can see that's an L2 thing. But if my memory doesn't fail, Carban does prove that the measure is in the continuous function between 0 and t and some vessel negative regularity space for the whole 0 to 2 square root over 2, for example. And you can understand a bit of it, but that's in another work of Christopher Carban. Dynamical review, it's called. Doesn't place.
So it should be the same regularity for both.
Yeah, I would expect that these are both are continuous as process from 0 t to vessel with negative regularity. Respect that for the regimes where they.
So none of them would be continuous as measure.
Yeah, they are going to the best space of negative regularity. They are including measures. Okay, now I understand.
Like
No, maybe I think
the weak topology.
No, I think you will need this extra, like this. I would, how to say it? You need to put a negative regularity vessel. Maybe that's more reasonable because you will understand the frequencies of each one of them. In the measure setting, I don't think you can do that. But yeah. I think that's all.
If there are no more questions, let's thanks for the guests. Okay.